Hello students, welcome back. Previously, we went through the modular vectors, and given integer x, before given integer x, let's suppose that the moduli m1, m2, m3, and so on, those are in place, and those are already in place, and they are pairwise relatively prime and everything. Suppose that the m part is already in place, and then given integer z, we can express it as a linear combination expression of this capital M and mu, mk and mu k, and all those are coming from the Chinese remainder theorem. Remember that. Mk is the multiplication, the product of all the moduli except the k2. And then for each mk, we can consider the multiplicative inverse of capital Mk modulo small mk, that's mu k, and all those are determined by the moduli m1 through mn. That has nothing to do with any selection of the integer. And then select the integer, and we get x1, x2, x3, and so on. Those are congruent to the original x, modulo m1, modulo m2, modulo m3, and so on. And then that association is one-to-one and onto, so that you can always get this linear combination expression one direction, and then we can retrieve the original back, not precisely, but modulo capital M. So that was the uniqueness, and that's how we use Chinese remainder theorem. And then through this, we can define modular vectors like this, and n-tuple expression, which is a shorthand of this linear combination expression. And then we can do the vector arithmetic, addition, and scalar multiplication, just adding up each component and multiplying scalar to all components. And then you can use this Chinese remainder theorem to retrieve the original entry back. And we went through an example problem like this. Yeah, x is 1, 2, 3, 6, 8, 4, y is that number, and then divide by 98, 98, 97, and 95 respectively, and take the remainders. So that's 33, 89, 9, and 89 respectively, and so on, like these. You can verify those with computer like that. And then you can do vector arithmetic, modular 99, 98, 97, and 95 respectively. And then using the Chinese remainder theorem, we can retrieve the original answer back, capital M1, capital M2, capital M3, capital M4 as usual, and their multiplicative inverses, modulo small mk, like these, and use those to get this linear combination expression so that you get the original answer back. Now, why would anybody do this kind of stupid computation while you can simply add these two numbers directly? The reason, any computer, no matter how expensive, have some preset memory limit. You cannot get away from that. It can be humongously large, but still there is a preset limit. It's man-made machine, so everything is finite there. So this mechanism actually helps us to do some humongous computation beyond the theoretical capacity of the computers into the manageable level. What we did here is computation, the addition of two 6-digit numbers, only with 2-digit numbers, because you see, input may be humongous, but all the computation got back into 2-digit numbers only, and then did the computation using only 2-digit numbers, we got the computation done. So 6-digit number input were made, and the computers has only capacity for 2-digit number computation, we can still do it thanks to this Chinese remainder theorem. Now, of course, modern-day computers are far more effective, so it can handle not just two-digit numbers, but it can hold up to 2 to the 35th power according to our textbook. And the textbook is written in sometime around 2010, I think, so maybe it improved these days. I don't know, but 2 to the 35th power is humongous already. Still, if your input is even bigger than that, such as some, 100-digit numbers or something even bigger, oh, wait a minute, 2 to the 35th power? No, yeah, so, yes, 2 to the 35th power is less than 10 to the 100th power. So, okay, all right. So if you have some really big number, kind of like Google kind of number, 100-digit numbers, and how do you do those kind of computation with the computers that can handle only up to 2 to the 35th power? Well, one way to do that is to set up these moduli, M1, M2, M3, and so on, so that you can use the Chinese remainder theorem to expand your capacity as you did in the previous example. You see, we use those 4 moduli, M1, M2, M3, and M4, pretty close to 100, so that you could calculate 6-digit number addition using only the memory limit of only 2 digits. And for 2 to the 35th power, what we want is some m values that are close to 2 to the 35th power that are relatively pairwise relatively prime. How do you get those? Well, our textbook gave us one quick way. M1 is 2 to the 35th power minus 1, M2 is 2 to the 34th power minus 1, and so on, 33 power minus 1, and 32 we skip it, 31 power minus 1, 29 power minus 1, and then big skip, 23 power minus 1, up to that, and we may need more, but let's just keep to those. Now, if those moduli are all pairwise mutually, all these mi's here are pairwise relatively prime, then we can use Chinese remainder theorem to determine any kind of vector arithmetic modular capital M, which is a product of all those moduli, which is bigger than 2 to the 184th power, according to our textbook. And I believe it, 35th power, 34th power, 33rd power, if you multiply all those and sum of all those powers, yeah, it's got to be greater than 284 at the very least. But the problem is, hey, are those really pairwise relatively prime? That's a new question. But the answer is yes. This 2 to the something power minus 1 form, those are so special that we know awful a lot already. It turns out the GCD of one such number and another such number is the GCD of the powers. So if the powers are relatively prime, then the 2 to that power minus 1, 2 to the other power minus 1 is relatively prime as well. Now look at these powers. The powers are 35, 34, 33, up to those, good. And 31 is a prime number, 29 is a prime number, and then jump to 23, that too is a prime number. So these are all relatively prime pairwise. So yes, we can use the Chinese remainder theorem, and then we can do the vector arithmetic, and then you can retrieve your answer back uniquely up to the whole number less than capital M, which is the product of all those moduli, which is greater than 2 to the 184th power. So basically, even your computers can handle only up to 2 to the 35th power. That's a memory limit. Using this modular vector arithmetic based upon the Chinese remainder theorem, we can improve the computing capacity to 2 to the 184th power. And computationally speaking, that's a big improvement. You see, how do you improve your computation capacity? How do you increase your memory capacity? You can build up new hardware, as a matter of fact, put more chips in there, but that's a really expensive way. If you can improve the software like this, that's much cheaper and far more effective. And the theoretical background, the tool for that computational theory is the Chinese remainder theorem, which was proposed in 1st century or maybe even BC. According to the written record, first proposed at least in the 1st century AD, and the proof appeared at least in 13th century, but quite probably it was around before that. That completes section 5, except for one thing, this lemma. You see, this moduli M1 through M6 must be pairwise relatively prime in order to apply the Chinese remainder theorem, as we have in the previous example 5.2. But in order for that to work, we have to have this, the proof of this lemma. But then again, here's the good news. We already did it. We already did it in lesson 2 when we studied the GCD. Part of the reason is this, because we're going to deal with 2 to the something power minus 1 here, right here in computation theory. Another purpose is, well, there are a lot of other uses for this 2 to the something power minus 1 form. The prime numbers of these forms are called machine primes, and then most of the humongous primes are found this way, and those are just 2 applications of this. There are many more, as a matter of fact, and that's why we studied this already in lesson 2. So we already did it, and if I give you a summary, it's kind of like this. If you do the division algorithm to those kind of numbers, then the same structure is preserved over to the remainder. Not the quotient. It is passed on to the dividend and the divisor and the remainder. Not the quotient, but nobody cares about the quotient because we are doing modular arithmetic. And then if you repeat that, then you're going to get Euclidean algorithm. So the same structure, 2 to the something power minus 1, is passed on to the Euclidean algorithm. Consequently, it is passed on to the GCD. And finally, as a result, it is passed on to the relatively prime structure. So these two are relatively prime if and only if the powers A and B are relatively prime. And that's what we use here in this lemma. So we are completely done with 5.3. And consequently, section 5, modular vector arithmetic, an important application of the Chinese remainder theorem in computation theory.